Good morning to all. I am Navneet Shibu. Today, I am presenting my EMERTXE internship project on EV ADAS dashboard using STM32 Bluepill microcontroller, Big SimLab for hardware implementation, and Python dashboard for visual representation. The objective of the project is to simulate an electric vehicle dashboard that displays real-time parameters combined with advanced driver assistance system ADAS. Their project combines embedded firmware running on the STM32 Bluepill. The hardware is being simulated using the Big SimLab, and a live visual representation was made in the Python dashboard. Uh, why smart EV dashboards matter? The modern electric vehicles continuously generates a enormous amount of data. This data cannot be controlled or evaluated by the end user. The parameters such as vehicle speed, battery states of charge, motor temperature, then the driving range and torque must be monitored continuously. The, as a result, we are building a system which analyzes the continuous change of this speed, brake, SOC, motor temperature, and does the required calculations and provide the accurate values of the range remaining, the faults, and also the ADAS values. The dashboard provides a real-time monitoring. It provides the real-time values of the speed, the state of charge of the vehicle, and the range tracking. It also makes the ADAS detection and provides alerts and warnings about the collision, blind spots, etc. Then the fault alerting. If there is any fault is detected, like increased motor temperature, the fault system will make the interrupt and alert the user about the same. It also makes critical alarms and advisory alarms. It provides various driving modes like the eco, normal, and sport. The system architecture of uh, our project includes mainly 4 stages: the sensors, the STM32, the UART 115200 baud rate protocol, and the Python dashboard. First, the analog sensors. Here we use the potentiometers for generating the values of the acceleration, brake temperature, and SOC. These sensors provides the values which are then converted, which are then given to the ADC of the STM32 Bluepill board. These values are then processed by the 12-bit ADC of STM32 and is used for making the calculations for the range and the mode, etc. The communication to the Python dashboard and to the outside world is via the UART 115200 protocol. Then finally, a Python dashboard is created where the data from the Bluepill board is given via the UART protocol, and the Python dashboards displays in a graphical manner, which includes the real-time speedometer values, the battery indicators, ADAS visualization, and live charts. The complete flow includes the sensors, then to the STM32 ADC, then the processing of these data, then via the UART to the Python dashboard. Slide 4 includes real industry versus our simulation. In our project, we focused to align our workflow to the real industrial environment. As a result, we use the same microcontrollers that is available, which is used by the industries, and also we done the visualization and implementation in the software side to reduce the overall cost and also to simplify the analysis. In our project, these hardware components are simulated using Big SimLab and potentiometers. Similarly, instead of a commercial vehicle display, we developed a Python dashboard that visualizes all vehicle parameters. Although the hardware is simulated, the embedded software architecture follows the same principles used in production automotive systems. This allows real testing without requiring expensive hardware. Then the project phases includes the development environment, GPIO peripherals, ADC sensor inputs, then goes to the EV dynamics model, ultrasonic ADAS, fault and alarm systems, UART telemetry, UART shell, and finally the Python dashboard. First, the development environment was configured using STM32Cube IDE, PixSimLab, and Python. And the second, GPIO peripherals were made and includes the LEDs, pulse width modulation buzzers, and timer interrupts. Thirdly, the ADC sensor inputs were given from the potentiometers for generating and giving the values of the acceleration, brake, and temperature. For the EV dynamics model was implemented to calculate speed, torque, battery charge, driving range, regenerative braking, and driving modes. Next, the ultrasonic ADAS uses the ultrasonic sensors HCSR04 for calculating the forward collision warnings, the blind spot detections, and time to collision values. Then the fault and alarm system. The fault and alarm systems are used to make the user aware of the faults like the increased motor temperature or the warnings like the collision warnings or blind spot detection alerts, etc. Then the UART telemetry uses the UART protocol at 115200 baud rate for transmitting the data from the microcontroller to the outside. This protocol is used for running the Python dashboard from the values from the STM32 board, then the UART shell. Then finally, we created the Python dashboard using the matplotlib, where we shows a graphical representation of the speedometer, the bird eye view, system of charge, and other parameters. From phases 1 to 4, the first phase involved setting up the complete development environment. STM32 Cube IDE was used for firmware development. PixSimLab simulated the hardware, and Python handled visualization. Multiple timers were configured for different purposes. Timer 3 is used for the periodic interrupts for sensor sampling. Then the timer 2 is used for the ultrasonic sensors. Timer 4 generated pulse width modulation for the buzzer. Then we uses the USART1 for the UART communication at 115200 baud rate. In phase 3, we created the ADC sensors, which are developed using the potentiometers. The acceleration is connected to the P0. Then the brake is connected to the PA1. Then the motor temperature is connected to the PA2. The ADC samples these inputs every 100 milliseconds. Using the timer 3 that is given to for the further ADAS processing. And for the further range and other calculations. Then phase 4, the EV dynamics model was implemented. The vehicle torque varies between 0 and 250. The regenerative braking produces negative torque when braking while moving, which recharges the battery and increases SOC. Vehicle speed is calculated using torque and vehicle dynamics. And the battery state of charge decreases accordingly based on the speed, the driving conditions, and the acceleration. Estimated range depends on battery charge and the driving mode. As we go to the driving modes, it has Eco, Normal, Sport. The Eco mode provides maximum efficiency, while the Sport mode delivers high torque but consumes more battery power. In the regenerative mode, if the brake is 5% more than the speed, then the negative torque is produced, which results in SOC. Okay. In the phase 5, we mainly focus on the ultrasonic ADAS engine. Here, we mainly uses 3 sensors, one to the front, one to the left, and one to the right. The front is mainly used for forward collision warning, and the left and right ones are used for blind spot detections. Using these values, we also calculate the time to collision and also used for parking assist. The thresholds set up for this ultrasonic sensors are like forward collision warnings activate if the distance from the forward vehicle is less than 50 centimeter and it becomes critical if it is less than 20 centimeter. Then the blind spot detection activates if the distance is less than 30 centimeter and speed is greater than 20 centimeter, 20 kilometer per hour. Then the time to collision warning activates if it is less than 3 seconds and it becomes critical if it is less than 1.5 seconds. Then it also includes the parking assist and overspeed advisory. Next, in the phase 6 to 7 fault system at UR telemetry, this a single 8-bit fault register stores multiple fault conditions simultaneously. The bit 0 is used for over temperature fault. If the temperature of the motor increases above 90 degrees Celsius, then this fault is flagged. Then if the SOC, state of charge of system, is less than 2%, then the SOC fault is flagged, which uses the 0x02. Then in the 0x04, the collision warning is flagged when the distance between the front vehicle is less than 20 centimeter. It also includes a fault sensor timer or a DUA timeout. Then the alarm system has 4 priority levels like the none, normal, it is made when the system is working normally. Then the advisory one, blind spot or speed above 120 km per hour. Then the warning is made if collision is less than 50 centimeter or TTC is less than 3 centimeter. Critical if collision is less than 20 centimeter or TTC is less than 1.5 second. Also the red flashes in the Python dashboard. So we go into the level alarm, for level alarm priority, and the UART frame rates. In the UART frame rates, we uses 115200 baud rate and is calculated every 100 milliseconds. It uses the frame like speed, SOC, torque, temperature, and range. Then in the next line, it includes the front, left, right, time to collision, blind spot detection, then alarm, and the fault value. Then at the phases 8 and 9, we implemented the UART shell and the Python dashboard. To simplify testing, a UART command shell was implemented. Instead of changing firmware repeatedly, parameters can be modified directly through serial commands. For that, it has commands such as the speed, SOC, then the temperature, modes, then fault, reset, status, etc. It allows rapid testing of different scenarios. By using these commands, we can directly change the speed of the device or the SOC of the device, temperature, and set up the temperature of the motor. And can be changed. The modes can be changed, and any faults can be cleared out, can be made, and system can be reset, and the status can be generated without making changes in the code. Then in the Python dashboard, it gets updated every 10 frames per second. It includes the speedometer. A circular speedometer displays vehicle speed. It has a gauge of 0 to 200 km per hour. Then SOC bar. It shows the live percentage of the battery, the range, the drive mode enabled currently. Then the ADAS per eye. It shows the top view of the car. Then the obstacle nearby, the time to collision values, blind spot detections, forward collision detections, etc. The speed history. A graph is also created based on the speed history. Then the EMERTXE, also the torque, temperature, alarm, fault, and UR status is also mentioned. Accordingly, we use the Python dashboard.py. Port in the port command is used for running the Python dashboard. Results and demo. The project was tested under multiple operating conditions. Speedometer updated smoothly in real time. Battery charge decreased during driving and increased during regenerative braking. Then the collision detection obstacle detected below 50 centimeter. Alarm escalates to critical at 20 centimeter with a red flash. Then blind spot monitoring. The blind spot monitoring is also worked at as expected. Blind spot detection reduces about 20 km per hour, and no false information was generated. The over temperature fault is also worked as expected. As the temperature of the motor increased to about 90 degrees Celsius, the fault is flagged and the LED is blinked. The Python dashboard, all 5 panel under. Okay, the Python dashboard has fully displayed all real-time parameters received from the STM32. The UART shell was also verified by injecting different parameters and faults through fixing labs. Overall, the successfully demonstrated a complete embedded EV dashboard with integrated ADAS inversion. Now we are going to see the demo of the project. For that, first we are checking the STM32 cube ID. This is my project file. This is the main.c file of the project. Here, the functions are created as separate functions, .c and .h functions, where they are then included in the main.c file. This is the ADAS.c file. Here, the ADAS calculations and the functions are described here. The TTC is calculated using these functions. Then forward collision warning is calculated here. Blind spot detection, this overspeed, etc. Then in the EV control.c file, there has the main calculations of the range, that speed, etc. Here you can see, like here motor torque is calculated, then the speed is calculated, regenerative braking is calculated here, instantaneous power is calculated, SOC integration is calculated here, estimated range is here. Then also the various states are defined here, like parked state, ready, driving, regeneration, fault state. Then in the fault.c, here the faults are identified and then flagged. If the temperature, the motor temperature is greater than threshold, this condition will be executed, and this is for the low SOC, and this is for the collision warning, like that. In the next ultrasonic.c, here the ultrasonic sensors are defined and their functions are carried out. Here we can see for how much time the trigger should be made, and for the echo, this is defining the timer for the same. Then find the UART shell. Here the UART connection is made to happen between the Python dashboard, and here we define how the stuff should be printed. Okay, then these all files are then included in the main.c file. We have called the ADAS.h, EB.h, EB.c, EB.h, ADAS.h. Then they are initialized. After that, this is the thing that is seen in the virtual terminal of the PixSimLab. Here it is defined. Okay, then after the code is written, and then we build the project. I have already done. After that, we open the PixSimLab for viewing the output. The builder project's binary file is loaded by clicking in the file load here. I have done it already. Then we can see the output here. This is the spare parts. This is the potentiometers for various controls like the acceleration, the brake, the SOC value, and the motor temperature. Then this is the left ultrasonic sensor, front ultrasonic sensor, right ultrasonic sensors. The left and right ultrasonic sensors are for blind spot detection, and the center ultrasonic sensor is for collision warning and collision detection. These are the various LEDs for showing the various states. This is the collision LED. This is the blind left LED, blind right LED, and fault LED. This is the virtual terminal where we can see the outputs. Now we can, the speed is 21.4, the SOC percentage 83.9, torque is minus 48, temperature front 347, 366, 354. It's being printed. Then if we, here the brake is now 40. If we increase the brake, then the value will be getting increased. Brake is 85. And if we increase the temperature, it will be increased. The temperature currently it is 32. Then the next print, we can see that it's increased. Yes, 31.9. Likely then, if we decrease the front ultrasonic sensor, we can see the collision and the fault LED is blinked, and we can see the fault 04 is being flagged, alarm 3 is being. Then if you decrease the left, this the left LED is blind detection is enabled. If you decrease the right, this is enabled. Next we can see the communication being made with the use of ESP. We have made the COM1 and COM2 pairs, and it is made activated. Then we have connected the same by setting the configure button and then setting serial port COM2 and fixing it up. And COM1 is then called. Then using command prompt, we have called the Python ev dash file to port COM1. Then we get the Python dashboard. What's this? Here it is the speed. This is the speed history by plotting the graph of the speed so at various time. Then this is the battery SOC. Then this is torque, EMERTXE. This is the bird eye view. Here the top view of the vehicle is shown. Then based on the changes in the this, we can see it's changed in the dashboard. Yes, if I increase the brake, we can see brake is increased. Then it will be updated here. Yes, it's getting updated 77%. Then if I decrease the brake and increase the motor temperature, first temperature, the fault will be triggered here. Yes, the fault is triggered, and here also 108, and the fault is shown here as increased motor temperature. And I decrease to the same, and if the collision warning is enabled, then the dashboard will become red, and from the bad eye view we can see the view. Then for the left and right blind spots, we can see two blind spots are shown here. That advisory warnings. Right. This is the overall working of the EV project. Now, I'd like to thank the EMERTXE group and my tutor, the Lakshmi Ma'am, for providing this internship. Looking forward for more such internships. Thank you.